Hello everyone, it's 1 p.m. Eastern Daylight Time, and that means it's time to begin another of our CoCoRaHS monthly Weather Talk webinars. Wow, this is our 29th webinar we've done in our series, and we're glad to have you with us today. I'm your host, Henry Regis. Behind the scenes today, running our technical side of the program, are Zach Schwalbe and Noah Newman. Joining me today is my colleague and CoCoRaHS founder, Nolan Duskin. We're coming to you live from the Colorado Climate Center here at Colorado State University in sunny Fort Collins, Colorado. Actually, it's a beautiful day out there. Nice warm temperatures here in the beginning of spring. Hey, for those of you who are unable to join us for our live broadcast, we'll be recording it for future viewing on our website. And all of our Weather Talk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, today we've got a treat for you. Our webinar will look at air quality from a local, regional, and global perspectives. And we're excited to have with us Sonia from right here at Colorado State University. She's in our Department of Atmospheric Sciences, and we're really glad to have her with us. Sonia and her research group study sources and properties and fates of particulates in atmosphere, including the role of invisibility, precipitation information, and climate. Sonia received her B.S. in Chemical Engineering from Manhattan College in New York, and then her M.S. and Ph.D. Degrees in Chemical Engineering from Caltech out on the West Coast. Sonia has experienced many different experiences with poor air quality from her early days growing up in New York City to her time in Los Angeles when she attended grad school there in the 1980s. And in fact, the Los Angeles air pollution sparked her interest in studying smog. A particular focus in her career has been to study how the transport of pollution to national parks affects visibility and how the reduction of visibility can be appropriated to various sources. Welcome, Sonia. It's great to have you with us today.
Thank you so much, Henry. Really appreciate it. And hello to everybody out there. Thank you all for listening in.
Well, we'll get your presentation up here in a second, and hey, this looks great. Well, take it away, Sonia, and we'll be back with at the end with some questions.
Terrific. Thank you. So when you read the title of this webinar and read air quality, you may have had a picture in your mind, something like this. We've seen a lot of these images and stories in the media about poor air quality and different challenges with respect to air quality in many parts of the world. And as you can see by these, air quality problems are definitely widespread. They can occur in large urban areas. They can also occur in more remote areas, depending on the local sources of air pollution and other issues such as meteorology. And one of the questions that you were asked when you signed up for the webinar was whether air pollution is a relatively new problem. We associate it with urbanization, increasing energy demands that put out pollutants in the energy production process. But we can go back into historical records and find that poor air quality has been a problem through the ages. And in fact, this illustration from the Netherlands in the 1700s shows that one of their local industrial processes was putting out quite a large amount of smoke. And many of these types of industries grew to be nuisances as people gathered in cities, and these types of activities became more concentrated. And one can go back in the historical record for a place like London and find through the ages there have been periodic bans on coal burning because air quality was deteriorating so greatly. And London, of course, has long been known for its mists and fog. By the 1800s, London was the world's largest city, and with the advent of the Industrial Revolution and the coal burning that had been prevalent there since the 1600s, it began to experience quite frequently what were called pea soup fogs. And the inset shows a Victorian painting demonstrating what that haze looked like to people of the time. So this was by no means a new problem, but going into the 1800s and early 1900s, the problem became very acute with the growth of the city and the growth of coal burning. And in fact, one of the watershed moments for air quality research happened in London around this time, and the word smog was invented to describe the air quality impacts that people were experiencing there. It was first used in 1905 to describe what was going on in British urban areas, and it is a condensation of the words smoke and fog to describe the combination of those two elements into what we know as smog. In 1952, London had a really severe air quality event, and these are images from that time. These are both during the midday, and you can see how severe the air quality impacts were there. Policemen had to lead buses around with torches because they couldn't see far enough to drive them about. And this smog event persisted for several days. It happened on December 5th to 9th in 1952, and it was characterized meteorologically by a stagnant air mass that had a very strong temperature inversion. This inversion meant that emissions that were being put out in the City of London could not be lofted and vented and blown out by the winds. They were trapped near the surface. A fog formed, and combining with the emissions from coal and diesel buses created one of these pea soup events. Because the event was so severe and so extended, during the course of 1 week, 4,000 excess deaths were documented. And this was really a watershed moment for air quality awareness among the public, and it really stirred a call for environmental action. And what happened after this in England were the Clean Air Acts of 1956 and 1968 and the City of London Act in 1954. One of the really unique things about this event was that we have actually data on what was going on. So if you look at this plot, you can see that during this event there were some rudimentary air quality measurements being made. These were basically filters being taken and weighed to get some idea of what was in that air. And as the stagnation event progressed, you can see how high the concentrations of that smoke in the air became. And correspondingly, people were keeping track of the deaths that were occurring in hospitals and people being brought into morgues. And you can see how those deaths corresponded very closely to the onset of that severe pollution event. After a few days, the weather changed and the smoke began to clear out. But you may have noticed in that red line that the deaths did not tail off to their pre-event days. And as this event was analyzed over the years following, not only were the 4,000 that were killed during the event counted among these deaths, but over 8,000 people who died subsequently from the effects of that air pollution event were among those attributed to this smog event. We had a similar situation occurring in the United States a few years before the London event in 1948 in Donora, Pennsylvania. Donora was an industrial town in Pennsylvania on the Monongahela River, and in the early 1900s it grew up very rapidly. There were a number of steel mills that located in the area. It was very successful industrially, and it boasted the world's largest zinc works. But the cost of this expansion was being felt in citizen complaints. Very early on there were complaints about pollutants that, quote, eat paint off houses. So it was perceived as very damaging to materials, injurious to people's health, and people noticed things like fish disappearing from the river. However, it wasn't until this event that happened in October that the severity of what was going on really became into people's consciousness. This picture is from noon on October 29th in downtown Donora. And like the event in London, there was an extended temperature inversion that trapped pollutants very close to the sources where they were being emitted, creating this very thick smog. And during that event, there were 20 confirmed deaths just because of respiratory issues that arose trying to breathe this air. Many of them were elderly or had existing respiratory ailments. But similar to the London event, it wasn't just the deaths during that time, but many more became ill because of this air quality event. Unlike London, we don't really have any data of what was in the air or what types of things people were exposed to during that Donora event, but we obviously do know that there were many health impacts from this, and it really raised consciousness in the United States of impending air quality problems. So it was a wake-up call, and many consider this to be the start of the invigoration of the environmental movement in the U.S., trying to look at what caused poor air quality and what we could do to mitigate that. Meanwhile, on the West Coast, Los Angeles had been growing up since the early 1900s and also was struggling with its own air quality issues. They do date back to the beginning of the century when industries were moving into the area, And people would complain about smoke and heavy emissions that seemed to be impacting them. But the key event in Los Angeles was this one on July 26 in 1943. And what happened was during midday there was suddenly a plume of what smelled like a chemical haze lofting into downtown Los Angeles, and visibility was reduced to less than 3 blocks. Because this occurred during World War II, some people mistook this smog event for chemical warfare, and there's a lot of alarm going on. Eventually became clear it was not that type of an event, and so the search was on to understand where this smog had come from. There was a nearby chemical plant that was blamed for these emissions, and due to public outcry it was shut down temporarily. Needless to say, the smog did not abate, and so it was clear that this was not the source of this chemical fog that people were being exposed to. So by August, the mayor went on record as saying that the search was on for understanding the culprits, and there would be an entire elimination of Los Angeles's air quality problem within 4 months of that time. So clearly Los Angeles has been dealing with this for many decades, and the problem was a lot more complicated than people understood at the time. A big question was, what was the source of this chemical haze? And really people didn't even know what was in that chemical haze. These images from that time show you some of the impacts. People could feel their eyes stinging when they went out in this. Obviously the visible haze was a big problem. There was a lot of open burning that went on in the area, and I've talked to people that grew up in Los Angeles, and this was a pretty common practice throughout much of the 1900s, just to burn trash in the backyard or in large landfills. And it took a long time from the event, in fact into the early 1950s, before scientists really explained what was going on in Los Angeles. And it turned out the air quality problem could not be attributed to a particular factory or some conditions at a plant that were going wrong. It was really attributed to the cars that were streaming into Los Angeles. Professor Ari Hagen-Smit of the California Institute of Technology is the one credited with shedding light on what was going on in Los Angeles and teaching us about the chemistry of smog. And he was the first to show in his laboratory that the smog was not coming from emissions from a particular source, but rather was being formed by chemistry in the atmosphere. He showed that the emissions, especially those from motor vehicles, could react in sunlight to create a chemical called ozone. This ozone is highly corrosive, and as it touches people's eyes and as they breathe it in, they experience irritation from this chemical, and that explained people's physical reaction to the smog. It also explained a bleach smell that people in Los Angeles had been complaining about during these heavy smog events. And his pioneering work was really the start of the field of atmospheric chemistry. So there are thousands of people over the world now that are studying what goes on chemically in the atmosphere, and that discipline really dates to his work in the 1950s. It's important to understand that it's not just the emissions, but also particular other things about Los Angeles that made it primed for having these severe smog events. You can see from this image that it is surrounded by mountains, and these help to trap the emissions in the Los Angeles Valley. It's also situated meteorologically under a semi-permanent subtropical high, which is responsible for many of the beautiful days of weather that Los Angeles experiences. But the clear sunny days are associated with high pressure, which causes large-scale sinking motion in the atmosphere. And as this air descends towards the surface, it heats and creates a layer of warm air aloft. Normally, as we move up in the atmosphere, the temperature of the air drops with altitude. This layer of warm air reverses that trend and is therefore called a temperature inversion. And this layer of warm air acts as a lid to trap the pollutants that are emitted in this region near the surface, where they can be held and built up, especially if this high-pressure event lasts for several days. Generally, it's cloud-free, and there's plenty of sunshine to drive the chemical reactions that cause smog. And so this is a typical setup. It happens not only in Los Angeles, but now in many parts of the world. And this type of smog is called photochemical smog because it's driven by the sun's light energy causing these chemical reactions. Why did Hagen-Smit blame cars? If we look at what was being emitted from cars, especially in the 1950s before many automotive emissions controls had been implemented, coming out of the tailpipes of those cars were a lot of unburned and partially burned fuel, or in other words, hydrocarbons. And these can also be released in petroleum refining. They can be released as we refuel cars and vapors come out. Pretty much any process that releases hydrocarbons puts chemicals in the atmosphere that contribute to the atmospheric chemistry that we're describing here. Those hydrocarbons have to combine with nitrogen oxides, and these are created from the nitrogen in the air during any high temperature combustion process. So in the internal combustion engine, temperatures reach high enough to form quite a bit of nitrogen oxides while the fuel is being burned. If these are not controlled at the tailpipe, they will be emitted along with these hydrocarbons, and then this particular mixture in the presence of sunlight is what creates ozone. So in Los Angeles, there are many emission sources, and all of them do contribute to the smog problem, but cars in particular were primed to create these high levels of ozone that people were experiencing. I wanted to point out that the formation of ozone by atmospheric chemistry is often accompanied by other chemical reactions that produce particles. So when we associate pollution events with haze, ozone is a clear gas, and normally we would not experience any visibility reduction just due to the presence of ozone alone. However, very often that chemistry is accompanied by particle formation, and so we get that characteristic haze that is seen in many areas with severe photochemical smog issues. So just to recap, this word smog now, although it originated for the London type air pollution, that was a combination of smoke and fog, and that was largely due to coal burning and those particular emissions. And like in the eastern United States, generally characterized by low-level inversions, cool weather, coal burning, and other industrial emissions, smog now is also used to describe photochemical pollution that was first identified in Los Angeles, where the chemicals involved are the hydrocarbons and NOx in the presence of sunlight, and in contrast to the London-type smog, hot, dry, sunny weather is very conducive to photochemical smog production. And we also associate with very high oxidant levels, oxidants like ozone that cause irritation. So these events that were happening in the mid-1950s increased people's awareness of both of these types of air quality challenges. And eventually, it led to the formation of the Environmental Protection Agency in 1970. And that was created to address U.S. air quality problems at the national level, rather than attempting to deal with this city by city or state by state. A lot of these problems, for example, automotive emissions, were really national problems and needed to be dealt with at that level. And this diagram explains some of the roles and procedures followed by the EPA in helping identify and mitigate air quality problems in our country. First question, as we found with the Los Angeles smog, is what exactly is in the air? And so careful observations and monitoring of air quality can help identify the different chemical compounds that are released in a particular air basin. The second question is understanding which of these compounds actually have harmful effects. So these can be human health effects like we discussed with ozone and respiratory and other irritation problems, or welfare impacts such as reduced visibility that can be dangerous to aviation, other types of travel. Can also be crop damage, which became associated with the presence of ozone as well. After we understand some of the harmful effects, then we need to understand at what levels risk is posed for each of the kinds of effects that we're looking at. And those studies will help decide what types of ambient concentration standards and what levels should be set so that these are not exceeded in the atmosphere in order to protect the population. And finally, to try to meet those standards, we need to look at how those lower levels could be achieved. And this is generally accomplished by proposing controls on the emission sources that we think are responsible. So for example, the Los Angeles experience helped us understand that we need controls on automotive emissions to begin to mitigate ozone formation and photochemical smog. And then finally, once those emissions controls have been in place, we begin the cycle again. We need to continuously monitor to see if emissions controls are being achieved and ambient concentration standards are also being met and achieved. And the other parts of this chart are also revisited as we learn more about what types of compounds may have health and welfare impacts and what concentration standards should be set to protect the population. What the EPA worked on and eventually established was looking at a number of compounds to identify as requiring these national ambient air quality standards. And if you go to the EPA website, you can find this table where it explains the compounds that have been identified and what the standards are. So let me take you through this table. In the first column, you find the pollutants listed that have rules attached to them. And in summary, there are 6 so-called criteria pollutants. 4 of them are gases, and they include ozone, which we've discussed, and nitrogen oxides, which we've discussed briefly, but also carbon monoxide and sulfur dioxide, and I'll talk about them briefly in a moment. And 2 are particle phase. In general, particulate matter is regulated, and we abbreviate that PM, and lead also is a criteria pollutant, and that shows up in particles as well. In the second column, we list primary and secondary standards, and what these mean are the primary standards are those designed, the levels that will protect human health, and the secondary ones are levels that will protect welfare, such as visibility, crop damage, and other types of issues. And in the last few columns, we find information about the levels that are to be met for the primary secondary standard, along with how to average observations to determine whether those levels are being achieved. EPA has recently summarized these air quality metrics in what's called the Air Quality Index. And these are calculated for each of those pollutants. And they're scaled so that when the air quality index is 100, we are just at the level of the standard that was in the table set before. So if we're well below that, the air quality will be labeled good, and as we're approaching it, it may be moderate. And then all of the categories that are above that moderate category have actually exceeded that ambient air quality standards, and the degree of the exceedance specifies how far above and how far into this table that particular event is being classified. And I'll have more to say about that towards the end of our discussion. I'd like to take a moment to talk a little bit more about each of these pollutants now. Starting with carbon monoxide, and this is a compound probably familiar to everybody. It's a product of incomplete combustion. And we know as we're exposed to that, we have different health effects that are felt, beginning with headaches and nausea. And for acute exposures, we can actually result in loss of consciousness and really long-term health impacts. And carbon monoxide was of high concern when automotive emissions were largely unregulated. Cars didn't run as efficiently and were putting out quite a bit of carbon monoxide. And with the emission standards that have been put in place since the early days of Los Angeles smog, this has become less of a concern. And there are still pockets of concern with respect to carbon monoxide. For example, boat engines don't have quite the emission standards, and sometimes people who are towed behind boat and being exposed to the exhaust can be exposed to high levels of carbon monoxide. And another time that we can have high exposures is when there's inefficient burning, smoldering burning, releasing a lot of CO, and this example here is a landfill fire. Lead is also a compound I'm sure is familiar to many of the people listening in. Exposure to lead, especially in children, causes a lot of neurological problems. And the primary route of people's exposure at the dawn of the EPA was through leaded gasoline. And as it was realized that the lead in the gasoline was being emitted to the atmosphere and could be breathed in by people, increasing their lead exposure that way, EPA began to phase down lead in gasoline in 1975. And this chart shows the progress we've made in phasing out lead used in gasoline, and at the same time, people's blood levels of lead were being monitored and showed a very strong correspondence to that phase out of the lead. So this is a success story. And there's also lead that was used in paint, and that has also been phased out of paint used in residential use, so that especially children's exposure to lead through that route has been mitigated. We still do national ambient air quality monitoring for lead, and you can see here the results of that monitoring for 13 sites. It shows the average and the spread of the distributions in every year. And from 1980 into 2012, we can see that there's been a large reduction across the country in the levels of lead that is in our ambient air. In fact, the major sources have totally changed. Automotive emissions are not a problem anymore, but rather most of our lead exposure comes from ore metal processing, like in smelters and incinerators. And aviation still uses leaded gasoline in small piston engine aircraft, and so what was formerly a very minor source has now become a more important source of lead exposure. I'll talk about sulfur dioxide and nitrogen dioxide together, and I've shown here a picture of a coal-fired power plant because coal burning is one of the major sources worldwide of sulfur dioxide emissions. Most forms of coal contain a small amount of sulfur, and as it's burned, the sulfur is released to the atmosphere as sulfur dioxide. And because the burning process is, again, a high-temperature combustion process, we also release these nitrogen oxides as part of that combustion process. So both of these compounds made EPA's list of criteria pollutants on their own because they are respiratory irritants. But perhaps more importantly, both of them will undergo further chemistry in the atmosphere. And where they end up is in the form of particles, so they contribute to that haze problem, and they also end up as compounds that contribute to acid rain. So emissions from coal-fired power plants began to be regulated in the 1970s as their link to acid rain was elucidated, and as point controls were put on power plants, we've seen emissions of these compounds across the country being reduced greatly. I also want to mention that this NOx we've already seen contributes to the formation of photochemical smog by contributing to ozone formation. These three species that I've circled here are what's termed secondary pollutants. And so unlike the SO2 and NO2 that are emitted directly, they're formed by atmospheric chemistry in the atmosphere. And so they pose a particular challenge to air quality improvement. We need to understand not only about the primary emissions that lead to formation of these species, but also all the chemistry and transport and transformation that goes on in the atmosphere, and how they are linked, how we can link emissions to the controls of these compounds. Because they're lofted for some distance downwind of these sources, before they're chemically converted, all of these compounds can have regional impacts. And one of the polling questions was asked whether only people in urban areas can be exposed to air pollutants. And the answer is no. Many of these happen on a regional basis because they are so linked to the chemistry that happens in the atmosphere. So here's what ozone looks like. It's a quite simple molecule. We've talked about some of the detrimental effects. It creates respiratory problems in many people depending on the level of exposure. It's also been shown to cause leaf and crop damage, and in conifers, for example, in the Sierra Nevadas that have been exposed to ozone repeatedly over the years, we see needle damage. And it's also linked with material damage. This is an example of a rubber gasket that was exposed to ozone and shows a lot of material damage. So this can be a secondary type of impact of air quality degradation due to a species like ozone. And one of the confusing things about ozone is that we hear a lot about the ozone layer, and that seems to be a good thing. So why is ozone being addressed as a criteria pollutant that needs to be regulated? And EPA has addressed this problem by coining the phrase good up high and bad nearby. So the ozone that we've been talking about as a component of photochemical smog is near the surface of the Earth where people live in the troposphere. And there is also a layer of ozone up high in the stratosphere above the levels at which aircraft fly. And this ozone layer is where the ozone hole is formed each year. It protects us from ultraviolet radiation. One of the properties of ozone is that it's very efficient at absorbing these short wavelengths of radiation, which I've shown by this cartoon here, and allowing only small amounts to penetrate to the surface of the Earth. So this screens us from harmful ultraviolet rays while allowing visible light to penetrate. A few things about particles. One of particles' main effects that we see immediately is that they affect visibility. And this is an image of a scene from a national park under 3 different loadings of particulate matter, and you can see how dramatically both the visual range and also the colors in that scene have been affected because the particles are absorbing and scattering sunlight and creating this haze that we're trying to see through. If we take a sample of particles in an urban environment, and this is from a city in England, and look at it under an electron microscope, we find a whole variety of particle shapes, a whole variety of sizes. This bar is just 5 microns in size, so this right here is much smaller than a human hair. We can see very tiny particles loaded onto this filter in addition to ones that are larger and micron-sized. And it turns out that the chemical composition of these particles, their sources, and also their health impacts are tied to their sizes. This cartoon illustrates that, where on the y-axis we have particle diameter in these units of microns. It's 10 to the minus 6 meters. And this shows typically 2 clusters of particle types in the atmosphere, ones that are larger than a micron in size and ones that are submicron in size. And what we find in these large particles are things like blowing dust. We find plant materials like pollens, and we find bacteria. As we look at smaller sizes of particles, we find particles that have been produced by combustion process, like those emissions from coal-burning plants, from automotive emissions, and so on. And at even tiny sizes, we may find things that have resulted from not only combustion, but also chemistry that occurs in the atmosphere. So the sizes of particles are very strongly linked to where they land up in our respiratory tract. On the x-axis here, you see particle diameter in microns, and you'll see following through this cartoon where different particle sizes are deposited in our respiratory system. So very large particles are screened out in the nose, mouth, and upper throat area. Particles around 10 microns or so can penetrate down into the thoracic region of our respiratory system, and even smaller particles around a micron end up lodged deeply into the lungs. This designation of particles of different sizes we call particulate matter less than 10 microns and particulate matter less than 2.5 microns. And these have become the particular focus of regulatory actions because of where they're ending up in our respiratory system and the types of chemicals that they can carry with them into those different parts of our lung. And it's been shown that exposure to particles affect not only lung function, but surprisingly also heart function, and this is not completely understood. The current theory is that inhaling particles creates an inflammatory response in our bodies, and that creates plaques in our bloodstream that end up building up plaques affecting our hearts and causing some coronary and cardiac outcomes. And the effects of particulate matter on human health were really brought home in this study from 1993. These researchers had particulate matter concentration data from 6 U.S. cities for several decades, and they began to correlate that to health outcomes, and this particular plot shows increased risk of death. And there's a very high correlation between more exposure to particles in the atmosphere and an increased risk of death. So this was really the impetus for a lot of our current regulations on particulate matter and allowable levels of public exposure. EPA provides this slide to give us a snapshot of the great effects that the reductions in emissions have achieved. Over the years from 1980 to 2012, we can see in the upper part of this plot, the U.S. has experienced a large growth in population and in things like our gross domestic product. While over this same decade, we've managed to achieve a decrease in about 70% of our emissions of those 6 criteria pollutants that affect human health. So this is quite a remarkable achievement, and it shows up in many ways in improved air quality across the United States during this time. This is a great visual to show you one example of that. It was put together by the improved team that works on monitoring visibility in the national parks. They're also located right up here at Colorado State University. And this is from studies between 2000 and 2008, and it shows you on an average day in Linville Gorge, North Carolina, the visibility in 2008 was like this, and in 2000 was like on the left, and by 2008 the average visibility had improved to what you see on the right-hand panel. There's still a lot of work to be done, however. If we count up the number of people in the United States that live in counties for which one or more pollutants exceed our national ambient air quality standard, there's over 140 million people that are exposed to unacceptable levels of pollution. And looking down at the criteria pollutants, we see some of them are really no longer of a great concern in this regard, including carbon monoxide and nitrogen oxides themselves, but others continue to be, and particularly ozone is a huge problem, and particulate matter. And this map shows where in the United States are counties that have failed to meet the 1997 standard for the fine particulate matter that's less than 2.5 micron, the particles that can penetrate most deeply into the lungs. And you can see why there's a lot of exposure of millions of people, although there is relatively few regions that have been flagged. These are in large large population centers across the United States. And we look at a similar map for the 2008 ozone standard. We see more regions of the country that are not meeting that ozone standard. And ozone is also categorized as the severity of the exceedance of the standard. One of the challenges looking towards the future as we attempt to decrease our emissions and meet these challenges of air quality improvement in some of these areas that continue to have poor air quality, we can see that, as I described before briefly, a number of these pollutants really aren't local. They have regional impacts. So in this imagery that is from satellite, we can see measurements of ozone near the surface. And these events are periodic and they travel, and we can see the ozone plumes moving across sometimes very large regions. And as you're looking at, in particular at the United States, we can see plumes of ozone that are coming from other parts of the northern hemisphere that can be impacting the air quality in the United States. So this rising background that is on a very large scale has come to people's attention. Here's a study that was published a few years ago where these researchers looked at sites that were quite remote. Many of them are in national parks along the western coast of the United States. And looking at these clean regions, we can see that the background ozone appears to have been rising over this time period from 1985 into the early 2000s. So this may be evidence that there is some rising background that is contributing to the U.S. air quality levels that needs to be considered as we develop control strategies. This study is also by the same group and shows another very interesting potential impact. This one is from fires that were occurring in Siberia. And in this upper graph, we see year to year there's a lot of variability in the acres burned in that particular part of the world. But there's a correspondence between ozone that was measured in British Columbia, in Washington State, and in Alaska, suggesting that there's a link between these increased fires and ozone being experienced in these parts of the western North America. And on the right panel, you see the results of a modeling study that show ozone enhancement due to these wildfires and that plume extending all the way across the Pacific into North America. Not just ozone, but particles have a long enough lifetime in the atmosphere to exert regional and global influences. This is a movie that was developed by NASA scientists from running a model of emissions of particulate matter and tracking them through the atmosphere. And they have several kinds of particles that show up here. The blue ones are sea salt that is being produced by high winds in ocean regions. The green comes from smoke, and you can see many of the world's large biomass burning regions emitting large quantities of particles. The red is wind-blown dust, and depending on the season, we can also see very large plumes of dust extending far out across major oceanic regions. And finally, what we think of as photochemical-related particles, pollution particles, are shown in white. And I'm pointing here to the eastern United States, where we see periodic plumes of these particles in air quality events and that are then lofted and brought across the Atlantic. Similarly, if we look in Asia, we can see periodic emissions and some of these particles being lofted out in transport events out across the Pacific. I wanted to focus a little bit on dust because it is a natural emitted particle type, but that can also result in air quality exceedances in the United States. And in this example, we're looking at summertime wind-blown dust from the Sahara region. And every summer, as these waves pick up convectively lifted dust from this area, it's lofted across the United States, across the Atlantic towards the United States, and very frequently impacts the Caribbean into Florida and actually many parts of the eastern United States. There have been some examples of air quality exceedances in Miami that can be attributed to the Saharan dust that is blown across in the summertime. We've also heard a lot in the media recently about these very large Asian dust storms that happen in the springtime. And these dust storms impact many of the countries in Asia over which they pass. And you can see here in the satellite image, this dust is being brought across the Pacific. And this frequently can be carried all the way towards the west coast of the United States and occasionally results in visible air quality degradation, even here in Colorado. In this particular example from Arizona, we see on the left an image with no dust impacts, and on the right what that same scene looked like in 2001 when we were under the influence of a major Asian dust storm. And finally, I wanted to talk a little bit about the role of fire in air quality. We saw in that movie that worldwide there are a lot of emissions from fire. And when we look at what comes off these large wildfires and agricultural fires, we have nitrogen oxides from the combustion process itself as well as unburned hydrocarbons. So we know these are ingredients for ozone formation. The combustion is highly inefficient, so we produce large amounts of carbon monoxide in most of wildfires and agricultural burning. And we also release large quantities of particles. So the potential for exceedances in the criteria air pollutants due to fires is very high. And fires are really a global concern. We know that there's many parts of the world where there's significant burning every year because of agricultural practices. But even looking across the United States, you'll see that many parts of the southeast have experienced agricultural burning, and many regions out west, year to year, have wildfires that go on and loft emissions into the atmosphere. So this beautiful movie that was created by NOAA forecasters looking at smoke emissions and their impacts across the United States was for a particular event in 2012 where there are a number of large wildfires occurring throughout the western United States. And as you track the progress of the smoke, you can see how far the impacts of the smoke plume extend, so that these air quality effects can be felt almost all the way across the country. It's a great concern for air quality managers because of looking ahead at what fires may look like in particularly the western U.S. in the future. And this plot dates back to 1918 and looks at acres burned in the western United States. And you can see that these dropped significantly in the early part of the 1900s. And this was due to our fire suppression policies, particularly in national parks and federal lands. This particular event is the 1988 Yellowstone fire, which some of you may remember. And once it was started, it raged out of control, burned almost unprecedented number of acres in that year, and it really brought to people's forefront what our years of fire suppression policy had meant. We were building up a lot of fuels in these regions, and so that when a wildfire was touched off, the potential for it to be highly catastrophic was there. And since that period, we can see that although there's a lot of variability, we have had a lot of severe wildfires that have happened. So not only the wildfires, but the strategies for managing these lands and perhaps doing more prescribed burnings to try to avoid these catastrophic fires is creating a lot of pressure for burning in the western United States and across the United States, and understanding those air quality impacts are really key. Another concern is that many projections that look into the future of a warmer, drier climate say that fires will only increase in the future, so these problems will continue to be ones that we have to deal with. I wanted to say a few things about some other compounds that I haven't mentioned that you may be thinking about with respect to people's exposure, and one of them is mercury. Mercury is indeed released by fossil fuel burning, such as can happen in coal-fired power plants, and it is transported in the atmosphere. But the real pathway of human exposure is through its bioaccumulation in fish, which are then consumed. So it doesn't qualify as a criteria pollutant and is not monitored in the same way as the other pollutants I discussed, but rather comes under the heading of air toxics. So there is a division at EPA that deals with these hazardous air pollutants. They've identified 187 compounds that include things like mercury and other carcinogenic compounds that are tracked. This is an example of an emissions inventory that was put together to try to understand where human emissions of mercury occur globally and to try to understand its cycling through the atmosphere and the routes of human exposure. There are also people that work in a lot of different occupations that are exposed to the same kinds of compounds that we've talked about as criteria pollutants, but very often the exposures are much higher and occur quite differently than the types we've been talking about. For example, in construction and in mining, people are exposed to high levels of particulate matter. Manufacturing can be particulate matter or other types of gases. And then in agriculture, where we also have high levels of particle exposure and exposure to different types of compounds. Indoor air quality is another area of concern. So some of these outdoor air pollutants can penetrate to the indoors where most of us spend a great deal of our time. And there's a lot of work that's been done to look at how pollutants penetrate, whether they're scrubbed as they move through some of the building materials. But it's also the activities that occur inside a home that can raise pollutant levels. For example, if there's any kind of burning going on or other emissions from chemicals that are used. And in your poll, you were also asked about whether worldwide exposure to air pollution occurs primarily through outdoor air pollution or indoor. And across the world, poor air quality that occurs through activities like this, burning of solid fuels indoors with inadequate ventilation, that is responsible for more premature deaths than the outdoor air pollution globally. So there's a lot of concern about cooking and other uses of fire and what we can do to try to mitigate some of the emissions from these types of sources. And I'd like to end the talk today by going quickly through some resources where you can learn about more of these issues, more of the science behind them, and more of the monitoring that goes on in your own backyard. And so EPA's website is a great place to start. If you click on Learning about the Issues and the Air tab, you'll bring up this screen where you can learn about the air pollution that we've talked about here, indoor air, more about acid rain, and climate impacts due to greenhouse gases. I'd like to say a couple more things about the Air Quality Index. We have a monitoring program that goes on throughout the United States that looks at levels of criteria pollutants. And each day these are compared to annual standards, and an air quality index is calculated for each of those compounds. And EPA reports the largest in each region for that day. And then the assignment of whether air quality is good, moderate, or wherever it falls in that category is made based on that largest index. So as I mentioned, the good and moderate means that all measurements have fallen below the ambient air quality standard, although moderate may be a flag not to go out and in the outdoors do things that require a lot of physical exertion, because as we do exercise outdoors, we process more air and we're exposed to more air pollution over a given time than if we're just breathing normally. The unhealthy for sensitive groups category means that we are just over that air quality standard, and some people in sensitive groups may begin to be affected. And once we move into the unhealthy standard, pretty much everyone will experience some type of impact from those levels of exposure. If you go to the AirNow webpage, this is where you can find the air quality forecast for that day across the United States. And you can hear more about wildfire smoke and advisories and forecasts from this tab here. And you can also input your zip code to find what your local air quality forecast is for that day. Here's one for the Fort Collins region. You can see I've gotten the southwestern United States a few days ago when I queried this, and it shows where air quality advisories and helps interpret what some of these air advisories may mean. And the other thing to point out is you can also find your state air quality resources under that tab. So I can go to my Colorado Department of Public Health and Environment website and actually find real-time data for all the monitors in the state. If you're interested on the larger scale, there's a website called DataFedNet, which processes and brings together in one place many types of air quality data. Here's an example of what the interface looks like, and so there are satellite data, model output, and a lot of monitoring data, including all the green are monitoring data sets that occur in near real time, including the AirNow database. And this is another way to access what's going on in AirNow. If you want to browse the data there, you can bring up interpolated maps here that show you the results, in this particular case, for all fine particulate that's monitored across the United States. On the AirNow, you can also calculate for a given level of pollutants what the air quality index category is, and it offers you some interpretation and practical advice based on that measurement. The Smog Blog is a really interesting website where this group of researchers at the University of Maryland go in and ingest a lot of these data from across the United States and find interesting air quality events to report on every day. So you can go through here and read narratives about what's going on in various parts of the country. And finally, on a larger scale, the World Health Organization provides information about ambient air quality, health issues, indoor air quality around the world. This is an example of their assessment of what particulate matter exposures exist in various countries around the world. And last, satellite imagery is provided by NASA through the Earth Observatory. You can subscribe to it using the link on this website. And this image shows a typical one where they've identified fires in Sumatra and the smoke that's blowing across then and affecting Singapore and other areas downwind of that location. And I'd like to end by mentioning that next week is Air Quality Awareness Week. This website at AirNow tells you more about air quality awareness, and the activities about that will happen each day next week. And I think Henry may be talking to you all a little bit more about Air Quality Awareness Week. So with that, I'd like to end and thank you for listening in, and be happy to take your questions.
Well, thank you, Sonia. This was very informative. I learned a lot just sitting here watching. Boy, I didn't know a lot of these things. It's really interesting. Folks, we are also putting links on our website to all of these different pages that she showed, so you'll be able to find that. We'll also have our slides, or have Sonia's slides available so you can go through at a slower pace and take a look at them on the website as well. I've got two quick questions for you. I was thinking about the the 6 pollutants that you talk about, the ozone, the lead, and so forth, which is the most dangerous of those 6 that the country's more concerned about? Is there one more than the other that they're monitoring and so forth?
I think that's a good question, and some of them do have similar impacts, but some of them are similar, like causing respiratory irritation, like we talked about. And I think in terms of which are the most concerned, it really comes down to the fact that so many people around the country are exposed to high levels of ozone that I would flag that as one of our major air quality concerns right now. You could see in that map there were a lot of locations where people are living in unhealthy levels of ozone, and particularly for those who have asthma or other compromised respiratory systems, exposure to high levels of ozone can be a real concern.
Another question, you know, I've sat in traffic before, and sometimes you'll get a truck or a car with a diesel engine in front of you, and boy, does that stink. And I wonder, is there a difference? Is one more pollutant or more dangerous than the other, or diesel compared to regular, or not regular, but unleaded gasoline in a car? So what do you know? Can you tell, is there a difference?
Sure, it's a great question. So normally we don't see any particles coming out of regular gasoline engines anymore with our emissions control. But diesel occurs at higher pressures and uses a different fuel, and so formation of soot is very common in diesel, and that is something that has been looked at a lot recently, and controls are being put in place now to control some of those emissions. But when you see a big plume of black smoke coming out, you're seeing particles, soot particles that are being created in that engine. And so those have all those health impacts of inhaling fine particulate matter. It's not a good idea to be exposed to those. Those can be quite different. So yes, diesel and regular automotive emissions are quite different, need to be controlled in different ways. And we began with cars, and we're moving now towards more controls on diesel to try to help mitigate those impacts.
Thanks, Ed. I appreciate you answering those. Hey, we've got some questions coming in. If you guys would like to type in a question for Sonia, do so. We'll try to get as many of those as we can get in the next 20 minutes. Chuck from Oregon writes, do we have chemical proof that the pollution from China has reached the West Coast? Is there any proof out there on that?
It's a great question. I think there's definitely events when the transport from really the whole Asian continent, when that transport is very fast, then many of the pollutants can survive to be detected, especially at high altitude sites. So it's not clear how much impact they have at the surface or in a place like Los Angeles. So we can detect signatures of these plumes coming across. It is not clear exactly what their impact is on air quality at the surface, where of course we're concerned about people's exposure. So I brought up the issue of rising ozone background because really every country in North America can be contributing to that rising ozone background. So our emissions are traveling all the way around the northern hemisphere, and it's not just emissions from Asia that might contribute to that. Right now, that increment due to that rising background is fairly small, but there is a concern as we try to push our air quality standard lower and lower. There may be a time where that becomes more of a concern, things we can't necessarily control within our own boundaries. There's a few other, like I showed you, the dust events that you can tell cross continental boundaries, cross ocean boundaries, sometimes fire events that can be detected. So individual events can definitely be detected at various locations. What their role is for our day-to-day air quality is much less clear.
Okay, thank you. Here Eva writes, and she wants to know, is there or are there any known links between weather phenomena frequencies such as hurricanes and tornadoes and air quality pollutants found in the air globally? So is there any kind of connection there?
That's a really great question. And in fact, one of the links that people are looking at now is between hurricanes and not necessarily a pollutant, but between hurricanes and the dust that comes off North Africa. So that dust appears to interact with the dynamics of the hurricane formation in some complicated ways. And so people are trying to understand those interactions. With respect to tornadoes, some people have suggested again that maybe windblown dust may be interacting, but none of that, it's very difficult to show. It really hasn't been shown what those interactions might be. And dust is a really interesting component of particulate matter pollution because it has natural sources from dry and arid regions, but human activities may be increasing those sources as we farm more land that's marginal or disturb land that formerly wasn't plowed. We can be lofting more of that dust into the atmosphere. So it's very interesting types of feedbacks between the natural environment and humans. I did want to mention with respect, you asked about air quality phenomena, one of the things that people are looking at going into the future is whether we'll have more high pressure stagnation events across the United States in a future climate, which means that more of those high smog events may be occurring in regions where air quality now is improving, but we may have the increased possibility of some severe events if temperature inversions stick around longer or happen with higher frequency. So that's a really interesting question looking forward.
Okay, thank you. Here's another one that has come in. Actually, a suggestion. Lance mentioned that the American Lung Association has a great app called The State of the Air that's out there, easy to use and in real time. So we'll put a link to that, Lance, if you could type that in for us. We'd appreciate that.
That's terrific. Thank you.
Yeah, appreciate that. Here's another question, and this is from Jeff. Jeffrey wants to know why the emphasis on CO2 emissions when regulating it. Could that lead to a drier, more arid planet? He says, hence more particulate matter and fires in drought regions. Seems you would want more CO2 leading to precipitation for further cleaning of the environment. And he thanks you for your insights on this.
Okay, thanks for the question. I guess if I understand your question, you're suggesting that more carbon dioxide leads to more precipitation, but I don't know of any link in that direction. It would be an interesting feedback. We know that more carbon dioxide does lead to warming in the atmosphere that's manifested in various ways. If some future climates involve more precipitation, you are certainly correct that then we would be washing out particulate matter at a higher frequency and washing out some of the precursors that would lead to ozone formation. That could even be a possibility as well. So at this time right now, the best we can do is to develop models of air quality where we put in our best known chemistry, best known emissions, try to understand how those interact with meteorology, and then look ahead into how meteorology might change in the future and what that might mean for levels of these criteria pollutants.
Thanks. Here's one from Adria from Oregon, and this is a really neat question. She said, like CoCoRaHS, we measure precipitation. Are there ways for citizen science to contribute to air quality monitoring? Are there any programs out there where they can do that?
That is a really great question, and I actually don't know of any, but I am going to take a look around, and we can put one on the website if we find some links for you to participate in. Thank you for that question.
Larry from Kansas writes, and he wants to know if the agricultural burning of grasslands in central and eastern Kansas is a major source of particulate matter in the lower atmosphere, and I guess that's just one of many places where that's going on.
That's right. Yeah, there is a surprising amount of agricultural burning in the United States. Burning generally occurs under very controlled conditions, so there's been a forecast that says it's a good burning day, and generally what that means is that we think the emissions are going to be lofted to higher levels in the atmosphere, and so they won't be trapped and won't cause widespread high levels of particulate matter. So they are certainly contributing some particulate matter to the atmosphere and contributing gases as well. Generally, they won't lead to local air quality events. They're designed not to. But again, as we control other sources of gases and particulate matter, especially in trying to control any regional air quality events, we're probably going to be looking at these types of sources more closely in the future to try to understand really what their contribution is. It's probably quite small compared to other things right now, but could become more important as we move forward and reduce some of those other sources. It's a really great question.
Well, here's one from Rick in Redondo Beach, California, and he's asking that you're familiar with Southern California's air quality. He wants to know if you're aware of specific hotspots downwind from major sources like the 40510 freeways or smokestack emissions. Have these receptor areas been mapped out as hazard zones? He says he sees many schools located in potentially dirty zones. And he says, thank you for the great presentation as well.
Oh, thank you so much for that feedback. And I haven't looked at the monitoring network in the Los Angeles area in a long time. I would suggest you can go to the AQI site and find some links to the local air quality monitors, and you'll find their locations, and you can look at reports from each of them for your area. So that would be a really great question. With respect to exposure, one of the results that has come out of EPA research over the last several years is that there is an increased risk of living within 100 yards of a freeway, because we do have a lot of particulate exposure close in to very large sources like the freeways in California. So there are new guidelines being put out for, if you are close to sources like that, some mitigation that can be done. So for example, children in a school, a filtration system can be put in place to help mitigate particulate matter exposure. So there are things like that that I believe, again, you can find them on the EPA website. If you have any trouble looking for something in particular like that, let me know. I'll try to help you navigate. But yes, individual sources like that or types of sources are being looked at more closely so that guidelines for people living and working in those areas can be put out.
And Mark just typed in here, he wanted to let you know that there are daily air quality forecasts for ozone, smoke, and dust for 48 hours. They're available at the NOAA website, the air quality part on that, and we'll put a link to that as well on our website. Thank you, Mark, for typing that question in.
Terrific, thank you. Yeah, and that is where I got that the movie that I showed of those fires impacting large areas of the United States from that NOAA forecast. It's really terrific.
Ruta up in Maine has a question for you. She wants to know, would you say that our air quality problems are because there are so many people now on Earth rather than natural pollutants? And your opinion on that?
Thanks, and that really is a great question. The more people, the more demand we have for energy. The more people are living in large urban areas, which concentrates emissions, so that we have these what are called megacities right now, and megacity pollution problems that are definitely on people's minds. The number of megacities has been rising, and the air quality in them, we know that there's a lot of work to be done in improving air quality in megacities. So certainly there are natural sources of many of these pollutants, but as people live in these large urban centers and live near many of these localized emissions, as I described to you, topography and meteorology often conspire to trap them close to the surface, and so people's exposure is definitely higher when we're living in these large urban centers. So these are definitely concerns worldwide, and reason that agencies like the World Health Organization are looking worldwide at these problems and learning from the lessons of our past 100 years and trying to look ahead to help improve air quality in many parts of the world.
Thank you. Here's another one from Chuck, and this is an interesting one. I know when I lived in Raleigh, North Carolina, we saw a lot of wood stoves and chimneys and fireplaces, and he says they've been recently under the microscope for air quality. What is the real concern with these wood stoves out there? What are they putting into the air?
Also a great question. And it is really particulate matter, to the best of my knowledge. I know that the Central Valley of California looked very carefully at wood burning and actually instituted wood burning bans because in the wintertime there, the meteorology was such that frequently fogs would form, trapping this wood smoke near the surface. There's a lot of interesting chemistry that goes on in fog water. and including processing of wood smoke emissions. And that was contributing to very high particulate loadings in that part of our country. And so I would expect that what you're facing in Raleigh could be very similar, especially in the winter time. These emissions can be trapped near the surface. The wood burning is not very efficient. A lot of particulate matter is being put out in combination with partially burned hydrocarbons that also result in particle formation when it's processed through fogs and in the atmosphere. So I think this is a particulate matter problem largely, although I would have to look at what was going on in your particular area in what particular season, but that would be my intuition on why that's getting looked at.
And Doug writes in and wants to know, does solar forecasting help in determining the air quality worldwide? So these different solar flares or different things like that from space weather.
No, I don't think that space weather has a very large impact. It's more just our regular weather forecasting that tells us if there are going to be areas of stagnation across the country where pollutants will build up. And when you find an air quality event, you'll probably find that this is a stagnation episode that's happened. And as it gets cleared out, you'll see that plume of pollution moving in the models and sometimes in satellite imagery being washed out. So it's generally much closer to the surface, the basically weather phenomena that would have the strongest impact.
And here it looks like our last question of the day. Xiao Zhang was wondering a term global warming, and he wants to know if, I'm not that familiar with that, but are there some linkages between global warming to air quality issues? Do you have any comments on how closely they're related?
I'm afraid I'm not familiar with that term either. So
Yeah,
I apologize.
I think he meant global warming.
Global warming,
Global
okay.
warming? Okay. And can you repeat the question, Henry?
Sure. There are probably some linkages between global warming to air quality issues. Do you have any comments on how closely they are related?
Yes. I alluded to that a little bit before where, people are looking at what does weather look like in future climates? So if we put more carbon dioxide into an atmospheric model and then predict weather systems, for example, what does that look like? And some researchers have found that there appears to be a feedback. As we're putting more pollution in and changing future climate, across the United States, for example, we project that there are going to be more stagnation events. There'll be warmer temperatures, which, when coupled with high levels of pollutant, really, can cause very severe health problems especially for sensitive populations. So, looking ahead, there is some concern that severe air quality episodes may be on the rise. Again, assuming current levels of emissions and pollutants are not reduced further in the future, then the existence of more of these types of meteorological events that encourage formation of pollutants through photochemistry, they may be on the rise.
Well, thank you so much. There's one more question just snuck in here before the wire. Do forests help reduce pollutants generally? Aaron writes.
So for our criteria pollutants, forests will interact most strongly with ozone. They can take up ozone. The primary effect is probably more of damage to the forest than actually real cleanup of the ozone levels that we would be talking about. So in general, the plants and trees really don't take up any of these pollutants. They can contribute some of the hydrocarbons that lead to ozone formation, and I'm glad you asked that question because it's a really important point that goes to air quality control strategies in many parts of our country, especially in the southeast where there's a lot of vegetation and warm temperatures. So vegetation there is actually, as part of the natural life cycle of the plants and trees, they're releasing hydrocarbons that can actually proceed with some of the same photochemical reactions as happening in the Los Angeles smog to create ozone. So part of ozone exceedances in that part of the country can probably be attributed to the high levels of those natural emissions. So control strategies have to really understand the relative contributions of natural emissions and the documented emissions from industrial processes and from cities and highways and in those same areas. It's a really difficult problem we can just really get at by modeling and trying to use the models to understand the relative contributions of each of these, but it is a significant issue to deal with when we're trying to design our future control strategies. So besides fire and this type of interaction with ozone formation, there are a lot of interactions between the natural environment and human activities that come under consideration with air quality. So thanks for that question.
Well, thanks. I've got one last question for you. This one may sound a little crazy, but I was wondering about cigarette smoke. If there's, there's been a big push to, we know it people that do smoke, it affects their lungs. What about affecting our air quality? I'm sure it's just a tiny component, but is there anything from, we've seen the difference of people that have stopped smoking. Has it changed anything, or your comments on that?
That is a great question. And as you say, it's more an individual exposure question rather than the types of ambient air quality that we've been talking about today. But it does remind me of a study that was done, again, at the California Institute of Technology in the 1980s, where Professor Glenn Cass and his group were looking at molecular markers in the air pollution to try to see if they could identify specific sources. And back in that time, believe it or not, they were able to identify nicotine in the smog and could apportion part of that smog to cigarette smoking throughout the Los Angeles Valley, which is just incredible. So I'm not sure that it was a very large proportion of the air quality problem, but you can, through these very clever, innovative techniques, you can actually detect signatures like that in smog. So these compounds do survive and become a component of the particles that we then breathe in. So in other parts of the world, I don't know offhand of any studies that have been done of contributions of tobacco smoking, obviously, to indoor air quality. That is a huge issue, and one that's recognized in the United States, that it has been banned in many indoor environments to protect people from indoor air quality problems.
Well, Sonia, we want to thank you for taking time out of your day today to give this great presentation. It was really great stuff. We appreciate all your doings here and what you put in. I'm getting a lot of questions, a lot of thank yous on our question people are writing in right now. So thanks again, and we really appreciate that.
Thank you so much, Henry. It was great. And do you want to remind people about the Air Quality Awareness Week again?
Yeah, Air Quality Awareness Week coming up April 28th to May 2nd, and actually next week, Earth Day. For those of you who on the 22nd, Earth Day is coming up. That started back in 1970 as well. So just some stuff coming up along there. We'll have a message of the day on Air Quality Awareness Week, running that whole week with different things you can learn about more. And again, these presentations are archived. We'll have them up later in the week, and you can listen to this again or go through the slides, and we'll put those links in. So, again, thank you. Well, I want to say please join us for our next CoCoRaHS Weather Talk webinar, and this one is coming up right around the corner in 2 weeks. 2 weeks from tomorrow, actually. This one will be on a Friday, and if you've ever flown on an airplane, you'll be sure to love this talk. So Friday, May 2nd, Mike Bardot and Rob Kazimark, both the aviation meteorologists, will tell us about aviation meteorology, everything from what causes clear air turbulence to how airport traffic control is impacted by weather. So be sure to sign up for that. We'll have that on the website and during on our message of the day shortly. And before you guys go today, please take a minute or two to take our survey at the end of the webinar. That'll come up. It'll help us know how we're doing. Again, thank you so much to Sonia, and for all of us here at CoCoRaHS headquarters, so long and have a great afternoon.